All right, so today we're going to talk about collisions. And give me a second here. So go ahead and write this down. So we're going to build on what we talked about last time. Basically, momentum is conserved, right? Just like energy is conserved. In other words, my total momentum, we should probably write that down here. Oh, that's so weird. It always takes a second for the pen to work. There it is. So weird. All right, so we should probably mention that. This is total momentum, initial and final. So it's the total momentum in the beginning and the total momentum at the end. So because the momentum is conserved, we could use that to figure out how objects are going to behave, especially if they collide into each other. So if an object, and remember, all these things are vectors, so there's going to be a direction attached to it. So you got to keep track of the formulas. If something's moving in the negative direction, you got to make sure you make it a negative. Because the math will tell you what direction objects will go in. And I think today we're going to go over inelastic collisions, which is a very specific type of collision. That's where they kind of stick together. The truth is there's a little bit, there's nothing that's, I got to think about that for a second. It's very rare that there's 100% or perfect inelastic or perfect elastic, but theoretically we'll talk about those things, okay? And so remember that because the momentum is equal to the mass times the velocity, we're going to keep track of two objects. This is the mass of the first object, mass of the second object, mass of the first, mass of the second. And we're going to keep track of the velocity of the first object in the beginning and the one at the end. Okay? All right, here we go. Everybody have that written down? Oh, I see somebody looking like this. Well, wait a second. Okay. Can we go? All right, cool. So now you don't have to write this down. I just want you to kind of look at the board and talk about this. So an interaction between two or more bodies in motion is a collision. So when we define something as a collision, don't think of like two cars crashing into each other. Just think of any two objects that interact, make contact. Okay, usually it is a type of collision. All right. So then think of these pool balls bouncing off of each other as one example. So anybody in here ever play pool? Raise your hand if you have. All right. So what happens? Did you just get here? Yeah. Yeah, it's okay. I saw you walk in. Never mind. So anyways, what happens is when you hit the cue ball, this little white ball here, and it collides into all the other balls, they go a bunch of different places. Now, we can track where those balls are going to go mathematically. Now, pool players do this naturally. They have certain spots that they want to hit the ball and how hard they hit the ball and all that stuff. But really, it is the conservation of momentum that determines the path of the ball. Okay? So atoms do the same thing. They repel each other in a gas, and this is a more important example. Okay? So atoms can have a charge. You guys learned that in chemistry, or well, maybe you didn't take chemistry, but in your 8th grade science, they probably talked about this a little bit: positive and negative charges. Like charges repel, and unlike charges attract. So these atoms can repel each other in a gas. So there's that. Even a comet rounding the sun is a collision in the terms of fundamental conservation laws. All right. So the momentum of the Earth is conserved because it's technically interacting, right? And you guys remember what type of force, the gravitational force between the sun and the Earth is? What type of force is that? Does anybody remember? Well, it doesn't make contact. So they're still interacting, right? But even though they're not making contact. Same with the atoms, okay? So write this question down. What is conserved in a collision and why? So we want to know what is conserved in a collision and why. All right, so to figure this out, does everybody have that question written down yet? Okay. So to figure this out, what's happening? So we've got two balls here. They collide into each other. What might happen next? Well, there are a couple of possibilities. So shout out what you think the possibilities are. Yeah. Okay. So I don't know if you could kind of pick up. So the green ball seems to have some momentum, right? That's why they draw this thing. It seems to have some momentum going this way. But the red ball has momentum, but it seems like it's just sitting still, right? You should be writing this down. And so one suggestion is that this green ball has a certain velocity, and once it hits the red ball will move forward, but the green ball will slow down. So that's one possibility. Okay. What's another possibility? And think of when you play pool. I'll throw one out there. One possibility is, depending on the situation, the green ball might go backwards and the red ball still moves forward. It depends. Okay. It really depends on how fast that green ball is going or how massive the red ball is. Another scenario is that maybe they both go together. In other words, the green ball and the red ball stick. And so they both go together. And when they go together, they have the same momentum or velocity, which would be lower than the original momentum or velocity over here. But in either case, the momentum is conserved, right? Does that make sense? All right. So let's see how that looks. Oh wait, did everybody get that written down? Now, pool players do this naturally. If you want the green ball to roll along with the red ball, there's a couple ways you could do it. You could either hit it really hard, you could put top spin on it, or you can hit it really soft. It just depends. But that's something different. Okay. Okay. Well, just like I said, the green ball could go backwards and it changes its velocity. Not only does it change its velocity, it changes the magnitude. It changes the direction and magnitude. Notice that these two velocities are shorter than the original velocity of the green ball. So this is the original velocity. This is in the negative direction, right? And then it's like the red ball absorbs that momentum. Okay. So that's one scenario. what is true about those forces? Well, the green ball is experiencing a force. You should write this down. So sketch this out first. Just sketch this little picture here. Just sketch this like this. So when you have a change in velocity, what's the fancy physics word for change in velocity? Anybody remember? Yeah. Well, that's a change in momentum. What's the fancy word for change in velocity? Yeah, I heard somebody over here who said that. Acceleration, right? So what's a mass times the acceleration? What's that? That's force, right? Does everybody have this sketched out? Okay. So there's a force. So remember that force equals the mass times the acceleration. And also, maybe you should write this down. Acceleration is the change in velocity over the change in time. So just write all this stuff down right underneath that. Okay. Okay. So what happens is, in order for the green ball to change its direction, it's accelerated. And in order for the red ball, remember, it's changing its velocity too. It has an acceleration going this way. And so this has a force going this way. This has a force going this way. Okay. And remember, the acceleration just means there's a change in velocity. The red ball had a velocity of 0. Now it doesn't. The green ball had a faster velocity in the positive direction. Now it's going in the negative direction, and it's going a little slower. The magnitude is decreased. Okay? So, I got to move my face. So we can, again, define our system where we want our system to be. Okay? In general, so draw a little box around it and say system boundary. We can define our system. We like a closed system, but we can define wherever we want it to be. So we're going to do slightly before the collision and slightly after, right? So you could say, let's write that over here. So like this is before the collision, and over here, my face is in the way, after the collision. We don't care about anything after that. We're just calculating right those two things. By the way, don't you realize that two roller coaster carts will collide into each other? Yeah, if they go down a drop and one roller coaster cart starts to go back up, it's going to slow down. Well, what's the roller coaster cart behind it going to do? It's going to keep going fast, and it's going to bump into that one a little bit, right? And so then it kind of, you got to figure all this stuff out. And you'll see in a second when we do our examples today why that matters. So write this down. In a closed system, no external forces act on the system, and the internal forces cancel each other out. So what's conserved? Man, this water is delicious. Now, this is all theoretical too. I should probably point that out. When we say no external forces act on the system, technically that's not true, right? There's air, unless you're doing this in a vacuum, so there's air resistance and stuff like that. But we're going to define that, right? Most objects, especially like a roller coaster cart, there's going to be friction between the wheels and the track and stuff like that. But theoretically, when we start to figure this stuff out, we're going to set up our system where we ignore external forces, right? And in this scenario, the internal forces cancel each other out. All right. So write this down. Did I go too fast? No? Okay. So write this down. The momentum before the collision equals the momentum after the collision. That's a big one. Now, energy can't be created nor destroyed. It can only be transformed. So that last sentence is going to be it's going to be something new for you guys since we spent so much time on conservation of energy. It says that the energy before the collision equals the energy after the collision, but the energy may be transformed. So sometimes what happens if stuff comes in contact with each other? Take your hands and rub them like this. Your hands are in contact. What happens? What do you feel? Heat, right? Heat is a form of energy. So when you come into contact with something, you're going to give off a little heat. So some of the energy is transformed into heat energy. That's just one example. Okay? And depending on whatever thing you're working on, if it's atoms floating through space or whatever, or the Earth orbiting the sun, all that stuff, some of that energy is transformed in those interactions. In college, they talk about this more. In fact, we rarely mention it in high school. We used to back in the day, but now textbooks don't mention it as much. So no energy transfer is 100% efficient. So when we go from kinetic energy to kinetic energy, you lose a little bit. Okay? Most of the time it's in the form of heat. There's other reasons. That's why perpetual machines can never really exist. You can never have a machine that creates more energy than it uses to create the energy. Right? So if you have a generator and you use something to make the wheel spin and turn the generator, you lose a little bit of that energy. All right, can we move on to the next thing? So write this down. There are 3 types of collisions. There are perfectly inelastic. Now that's like the clay ball. Remember that? So I'm going to give you some examples that we've covered over the last couple of days. Remember we had the clay ball that we dropped it and it just splatted? Or we'll say ball of clay. So when the clay hit the ground, it just splatted on the ground. It collided with the ground, but it didn't bounce up. So that's perfectly inelastic. Inelastic kind of sticks. And so when we talk about inelastic, one way that let me, I liked, this is how I remember what's what. So inelastic sticks, and this is how I remember this, and it's kind of corny, but it helps me. Stick has the word, or has the letter I in it. Inelastic starts with the letter I. Okay? That's how I remembered the difference between the two. Now, elastic doesn't stick at all. In fact, if you look at the path of the inelastic, it bounces here, bounces up to the same height. So perfect elastic collision, all the momentum is conserved, all the energy is conserved, nothing gets used up. Well, not all the energy is conserved. Okay? So that's the elastic one. Okay? And today I think we're focusing on just the inelastic ones. Those are the ones that stick a little bit. Most things stick a little bit. Does everybody have that written down? Okay. So in a closed system, and you guys need to write this down. So in a closed system, momentum before, actually, just write this down, and then the next couple slides you won't need to write down. But just write down, in a closed system, the momentum before the collision equals the momentum after the collision. And again, we should probably mention over the word momentum, put total momentum. And then over here, put total momentum. And we always use the subset notation, I for initial and F for final, right? And we'll use that for the velocity. The masses never change, at least in the examples we're doing. Can I move on to the next slide? Now, you don't have to write this down. I got to move my face again. But I just want you to kind of look at the screen and read along with me. It says calculate the unknown momentum for the object before the collision. So this is how you solve these collision problems. So you almost always calculate all of the momentums, right? The sum of the momentum. Then calculate all of the known momenta, that's plural for momentums, for objects after the collision. So a lot of times you're going to calculate the initial, they're going to give you a bunch of information, then you're going to be expected to calculate the final, right? Before and after. Then equate the total momentum before the collision to the total momentum after. Equate just means make sure they equal. You're going to set them equal. Then solve for the unknown momentum. Okay? And so this is, don't write any of this down. We're just going to look at this real quick. So we have two objects here, this mass and this mass. They collide into each other and then they stick. And this is important. They stick. And write this down, maybe, just this sentence right here. They stick, and that means that they will have the same velocity. So if they stick during the collision, their velocity is going to be the same. Okay? So they're going to have the same velocity. Actually, it's going to be the same final velocity. Well, actually, don't write that down because we did an example problem. Don't write the final velocity because we did a problem the other day where it was the initial velocity. Okay, but what you do is you're gonna basically let's just kind of go through this real quick. You take the mass of the first object, the initial velocity of the first object, mass of the second times the velocity of the second and the initial. And remember that you've got to do, if it's going in, remember this is the negative direction, this is the positive direction. So if it's going this way, it's positive. If it's going this way, it's negative. All right? So kind of keep that in mind. And then you're going to set up these equations like this. And then it says, which term can we get rid of in this equation? Well, at the end, you're going to get rid of m2 because this velocity, the initial velocity of 2, is equal to 0. It's not moving. You see how the green one moves in and the red one kind of sits still? So 0 times the mass is just going to be 0, right? And then over here, they have the same final velocity, like I said, because they're both traveling at the same velocity. So then you just add up their masses and then go from there, okay? And so usually we know the masses, and we'll probably be given the initial mass of the first ball and stuff like that. So let's do a problem of this, all right? So now I need you guys to write stuff down. So a green ball has a mass of 5 kilograms. Well, let me use the right color. A green ball has a mass of 5 kilograms and a velocity of 10 meters per second. All right, so I'm going to say, and I like to draw the visual, so I've got this green ball here, and the mass of the green ball, 1 equals 5 kilograms, and it has a velocity equal to 10 meters per second. And because it's positive, we're going to assume that the green ball, well, let me draw it over here. The green ball over here is moving in this direction at 10 meters per second. The red ball has a mass of 15 kilograms and is initially at rest. So we have the red ball here. It's not moving at all. So the mass of the second ball is equal to 15 kilograms. And then the initial velocity of the second ball is 0 meters per second. Okay. Whoops. All right, so how do I do this problem? Well, whoa, where's that? Right here? All right, what the heck is going on with this thing? So the first thing I need to do is I know that the mass of the first object times the initial velocity of the first object has to equal the mass of the first object times the final velocity of the first object. I think I wrote that backwards, but you get the gist. And then we do the same thing with the red ball. We have the mass of the second object times the initial velocity of the second object. And over here we have the mass of the second object times the final velocity of the second object. Well, because this equals 0, so now let's just plug the numbers in, okay? So the mass of the first one is 5 kilograms times 10 meters per second. Plus 15 kilograms times 0. Then over here, we're gonna change a couple things. Since they stick together, we know that they have the same. So VF1, that's the number 1, is going to equal VF2. So we're gonna put the masses inside here, and then we're just going to multiply them by VF2 because they have the same velocity. Okay. Or you could just leave it as VF. It doesn't matter. So then what's the mass? Well, the mass of the green ball is 5 kilograms plus the mass of the second ball, which is 15 kilograms. Okay? Well, immediately this times 0 equals 0, right? This over here is going to be 5 times 10, so this is going to be 50 kilogram meters per second. Over here, I'm going to have 20 kilogram meters per second times V sub F, right? Oh, actually, it's just 50 kilograms, right? It's not meters per second. It's just 20 kilograms times VF, right? So then I got to divide by 20 kilograms. Wait, did I get everything right? Yep, positive, negative, or anything. I think so. So this cancels with this. Kilograms here cancels with the kilograms here. Does anybody know off the top of their head what 50 divided by 20 is? Isn't that 2.5? 2.5 meters per second is equal to my final velocity. Okay. So what's nice about the inelastic collisions when they stick together, and again, remember when we say stick is the same as inelastic, right? We've got that I right here. So I'll leave that up there for a second. Does anybody have any questions? Can I move on to the next slide? We're almost done with our notes. I see you guys starting to drift off. Starting to sit like this in your chairs. Heads are leaning to the side. All right, let's go. Hey, guess what? We're right. Now, they did all the algebra work first and then plugged in the numbers last, but whatever. Okay. So you don't have to write this down. Well, actually, you do. Write this down. Define a perfectly inelastic collision. Well, in a perfectly or totally inelastic collision, two objects stick together after the collision. There is only one final shared velocity. So in your homework today, we're going to review a couple of problems on calculating momentum and stuff like that, and impulse. But the new questions that you're going to have are going to be all inelastic collisions, I think. I hope. I can't remember. For the elastic collisions, those are a little harder sometimes because you have to calculate two velocities, so you need two equations. And then, oops. Is everybody done? Can I move to the next thing? All right, so same type of problem. This is M1, 10 kilograms. It's moving with a velocity in the positive direction. So this is V1 initial. That equals 3 plus U meters per second. Strikes a second stationary. Second stationary tells me that the velocity is 0. And then the mass of the second object is equal to 10 kilograms. So I'm going to go through real quick. I'm going to go a little faster. So remember that PI is equal to P final. Remember that M1 times V1 initial plus M2 times V2 initial, okay, has to equal M1 V final 1 plus M2 V2 final. Okay? Since V2 final is 0, this whole thing goes away to 0. Since V1 final equals V2 final, then I can just down here put M1 plus M2 times V final. And that's what they want us to find, is the final velocity after the collision. So then over here, I just need M1 V1 initial. So M1 is 10 kilograms times positive 3 meters per second. And that's equal to 10 kilograms plus 10 kilograms times the final velocity. So I get 30 kilogram meters per second is equal to 20 kilograms times V final. You guys should be writing this down. Divided by 20 kilograms. Those reduce down to 1. And I get 20 kilograms over here. The kilograms reduce. And then our final answer is just, isn't that 1.5? Positive 1.5 meters per second. That's our final velocity. Does everybody have that written down? Just wait a couple seconds here. Did you guys do the show last night? Okay. Okay. What, parents' night last night or something? Okay. We good? Okay. So, yep. Turns out we're right. Yay. So now, I'm not going to write all this out because you guys already know how to do kinetic energy, and we're running short on time. So I don't need to explain what's going on here. But if we do the kinetic, if we calculate the kinetic energy in the beginning, the only one that has kinetic energy is the first object, right? But then if we calculate the kinetic energy at the end, what do you notice about the kinetic energy? So what I do want you to write down is just kind of say kinetic energy before the collision, 45 joules. After the collision, 22.5 joules. Why is that cut in half? Well, because the two balls stuck together and they have the same velocity. All right, can I move on to the next slide? Now, also, probably should mention, is the kinetic energy conserved? And the answer is no. Sort of. Well, don't say no. It's different. Basically, we have to figure out where that kinetic energy went. What's it go towards? Oops. Well, somehow I deleted all the stuff. Was that the end? I guess it was the end. Did everybody have that stuff written down? Okay. No? Well, guess what? I'll put it back up here. So the only thing we need to write down is what is the kinetic energy before the collision, 45 joules. After the collision, 22.5 joules. Was the kinetic energy conserved? Well, the kinetic energy isn't, but the energy is. That's a better way to word it. All the energy is used up somehow, some way. So I'll give you the short answer since this is the end of our slides. The short answer is that some of that energy is used to keep them stuck together. That's one way to look at it. All right. Are we good? Not yet? Okay. All right.